Hello. All right. So I think we can just start. Yeah, welcome to the second lecture. It's gonna be on kinematics and statics, both in the linear case and the rotational case. So kinematics and statics, linear and rotational. So it's kind of like a hodgepodge of like both. So we're gonna be going quite fast today. So hopefully you guys are and we will have handouts at the end. Um, so yeah, like just keep in mind. So in today's thing, we won't be talking we won't be talking much about forces. We won't be talking about like functional forms of forces. We'll be talking about how we can use ideas from last week, vectors, math, coordinate systems, to model whatever like we want to study. This can be in terms of kinematics, where you slap a coordinate system and model how things move, or you can be like in statics, where like you can use the idea of vectors and like say that they all add to zero. So we're talking about a few things today. So yeah, like I think before we start, it's good to recap like what we talked about last week. So can you guys remind me in a two-dimensional space, what kind of coordinate systems do you have? A two-dimensional space.
Cartesian and polar.
Yes, sir. Yes, thank you. Cartesian and polar. So for Cartesian coordinates, thank you, Kite. This is exactly x, y. Sorry, that's And in the polar coordinate system, we have this r theta. So even though we still have this like horizontal, yeah, so we'll be calling this like r theta. So suppose you have some random vector, there's gonna be x and y components. But for r theta, you just have to specify where you measure the theta from. Um, Yeah, so you just have to specify where you measure data from. So this line can be anywhere. This doesn't have to be on the x-axis. It's just like by convention it is. If you go to three dimensions, you have to be a bit careful because it's not the x-axis anymore. It's the polar angle. So if you go in three dimensions, the spherical coordinate system has this as data instead of this. So just a little nuance, like don't worry about it. We'll be going to 3D maybe in the future, but yeah, for now, like we're just like focusing on the polar coordinate system in 2D. Um, for today at least. If you go into astronomy or stuff like that, then the spherical coordinate system would be useful. Cool. Um, so just to recap, if you want, so like, for the Cartesian, I'll use X, Y, Z. And polar, I'm going to use r theta and then assume everything happens in a plane. So r theta is zero. So essentially, it's just a two dimensions. Why am I doing this? Because in today, when we talk about rotational stuff, we're not talking about dynamics yet. We're just assuming everything stays in one plane. So everything stays in the XY plane, and then if neither, we'll like go to the third dimension. You'll see. So so yeah, like if you have something in XYZ, if you want to represent it with a vector, you could call that point P, say that that point is XYZ. Or you can also write like x hat plus y hat plus z hat. I like to use this way. I like to represent my vectors this way. It's like how, but there's no right or wrong answer. It's just like how you like your eggs in the morning. Um, so it can also be I, J, K, and still be the same thing. It's just the different conventions. Like I like to use the second one. Sometimes I use the first one. I don't hate the third one, but I just don't like it because you have to remember, okay, which one's I again, which one's J again. But X, Y, Z. Like just remember that. This X hat, Y hat, Z hat that represents the unit vectors. Oh right, I forgot to mention unit vectors. So whenever you see something with a hat, it's always something that has magnitude equal to one. It's only there to represent orientation. The hat vectors. So suppose you have so x hat, y hat, z hat. The hat vectors are there to represent orientations and orientations only, which is why they're so useful. I'm not saying this is not useful. This is also equivalently useful. I'm just saying that like when you take derivatives, when you take like integrals, sometimes the unit vectors may change. So you have to be a little bit careful. So yeah, so these are unit vectors, and um, they have magnitude one. They're just there to represent orientation. Um, yeah. So oh, wait, sorry, one more point. They might change in time, depending on what your system is now. Normally in XYZ coordinate system, the unit vectors are going to be the same. But let's take a look at what happens in the polar system. So in the polar system, oh wait, one last thing about unit vectors. They are the direction where when you change a coordinate by a little bit, that's where the vector will change. So what I mean by that? So the reason why x hat is this direction, the reason why x hat is this direction, the reason why x hat is in the pointing to the right is because when I change x by a little bit, by definition, by my setup, the point will move a little bit to the right. It's kind of trivial to say in this case, but in a polar coordinate system, it's non well, like it's not non-trivial, but like, you see things more clearly. And this is the definition in multivariable as well. So let me pull this down. Okay. So when you change x by a little bit, this point goes to the right by a little bit. So that's why that direction is x hat. If you change y by a little bit, the point will go up a little bit. And that's where y hat will change. That's where y hat will point. It's trivial, I know, but like, this definition. It's gonna be useful like when you go to university and then you see, oh, like this is what I learned before. They will do this in math class, basically. Um, so in the polar case, when you have arc data, where does r hat point? Someone illuminate me or point me in the right direction. Get it? Because never mind. Anyways, so r hat will point in this direction because when you change r by a little bit, when you change r by a little bit, this point will go outwards radially by a little bit. So see, the thing we're talking about here is orientation. We don't really care about magnitude because we know that unit vectors always have magnitude one. We don't give a shit about that. We only care about where the orientations are. Like where it points, where it starts. Well, like yeah, where it points is what's important. And if you change theta by a little bit, where does it go? If you change theta by a little bit, the whole thing like rotates by a little bit, right? It rotates by a little bit. Kind of looks like it's perpendicular because it is. So this would be the theta hat direction. And this idea of like changing a coordinate by a little bit and see where it goes, it's it's useful when you have a really like unfamiliar coordinate system. But normally that's not the case because like these coordinate systems are supposed to be tool sets for you. And if you're not familiar with a tool, don't use a tool. So there's many ways to solve the problem. This is just one of the ways that like this is one of the tools that you may or may not use. So yeah. And when you want to represent a point, so similar here, if you want to represent a point in polar coordinates, you can use um, you can use this R data representation. Um, I personally like this one more. It's just R hat. There's no data in data hat. Um, so let me illuminate why that is. So okay, one more thing. Because last week we did dimensional analysis, these unit vectors have no dimension. These unit vectors have no dimension. Remember, these things are dimensionless. These things have no units, right? So in polar coordinates, it's a little bit funky because R has R is something that has units of length, right? Theta is theta is an angle. Let's remind ourselves real quick. Do angles have units? And if they do, what units are they? Are they meters? Radians? Yes, sir. They are radians. So essentially they are. So they're different. They're yeah, or gradients if they're curves like that. But um, oops, sorry. Um, so yeah, like you have to be a little bit careful because the units are not the same. So you cannot write something like this. This thing is wrong. You can't write something like this. Number one, the reason why it's wrong is because it's dimensionally not correct. The units are not the same. This thing has units of meters, but this thing doesn't have units at all. So it's a little bit funky. You can't write that. Um, what you can write, however, is just this R hat. And you might be like, so where the data go? Like, where's the data? The data is actually secretly wrapped up here. The data is secretly wrapped up here in the R hat. Right, because this R hat only points in a direction that's a theta away from the horizontal. So do you see this? R hat. It's theta away from the horizontal. So like that's kind of an implicit function of theta. So yeah, like this is a case where a unit vector might change depending on the other coordinates. Um, so yeah, like be a little bit careful. They still represent orientations. They still represent like unit vectors of magnitude one. It's just that now they're not always constant. They by the setup, they will most probably change. Cool. Any questions so far? One last thing, I want to remind ourselves of cross products. So, what's the cross product of y cross x? What's the cross product of y and x? X hat and y hat. Y hat cross x hat. Friends, what is the cross product of y hat and x hat? I did not wake up at 7 a.m. to get zero response. Close, Jungwei. It's not z. It's negative z. That is right. Thank you for catching yourself. So, why is it negative z? Let's remind ourselves. So, you use a right hand rule. You put your right hand, you put your right hand, um, you put your right hand in direction of y, and then you cross it in the direction of x. So, where does your thumb end up? Your thumb ends up into the page. So, thumb ends up into the y cross x direction. Well, to be honest, like depending on who you ask, Z or negative Z is like not wrong lah. Like some people say it's Z, some people say it's negative Z, because there's two coordinate systems like still, but I think it's close lah. So sometimes if you look at textbook, they might use this like curse notation. So normally I like to do it like this. So it's like X Y, and then this would be Z, right? Some people use X Y. And then Z. It's not wrong. It's not wrong. It's just a little bit cursed because that means that y cross x is equal to z, and then it's just I don't know. It's a convention thing. Like you never. It's like velocity is always v, acceleration is always a, stuff like that. Um, it's not wrong, but this is called a um positive orientation. I don't remember positive convention, and this is called a negative convention. I mean, the point of the matter is like it doesn't really matter as long as you stick with it, be consistent, it should be fine. Anything you can do with a coordinate system, you can also do without a coordinate system. Um, so actually no, like that's wrong. Anything you can do in one coordinate system, you can do in another coordinate system. So yeah, left-handed. I mean, the point is that it doesn't really matter as long as you're consistent. It should be fine. So no, I like to stick with this, and this will be assumed throughout the handouts. This is not wrong. This is not wrong. I'm just saying like I'm not used to it. So and I think like frankly speaking, just stick with one, and like many textbooks use the one on the left. So yeah, cross products. Any questions on that? We all know how to write cross products. Okay. Okay. So, one last thing. Because we're using a 2D polar coordinate system, the polar coordinates are in 2D, it's in a plane. So if I take two vectors in this plane and I take the cross product, where does the vector point? So if I have so if I have P1 cross with P2, So just two vectors in the xy in the r theta plane. Where would this point? Yes, so like in the perpendicular direction. It's perpendicular to the plane. Okay, cool. Enough review. Let's get started. Okay. Again, if you have any questions, if you just like let me know anytime. Cool. So the first thing I want to talk about is the changing coordinate systems. As I alluded to before, when you have a polar coordinate system, when you have a polar coordinate system, um, yeah, so when you have a polar coordinate system, how do things change in time? So, what do I mean by this? So, what I'm trying to say is that when you have a vector in x, y, z, you can easily represent the vector p as x of t, y of t, z of t, right? That's just how it is, and you can also say that it's this thing. Yeah. So, like when you have a rectangular system, you can write this. But what about in a polar coordinate system? It's a little bit different now, right? Because in the rectangular system, if you want to take a time derivative, for example, if you want to take a time derivative, it's just the component-wise time derivative. So see what I did there? When I take the time derivative, it's only the components that change. It's only the components that get like taken the derivative of. You see that? But it's a little bit different in polar coordinates. So let's see how we can do that. So suppose I'm in a system where data changes by time. So this data like increases so this thing's gonna spin around in circular motion, right? So let's say I have this thing that spins around. How would how could we represent that? So this is a simple case. The simple case that like data can change. The even more complex case is when even R can change. So let's take a look at that. Like what happens when R and data can both change? So we said that P can be written as R hat. So when I take the time derivative, the nuance here, the caveat that you have to be careful of is that R hat is also a function of data. R hat is a function of data. So there's going to be R prime R hat plus R hat prime. I'm just using the product rule here. Left d right plus right d left. Du dv plus v du. The product rule. So it's a little bit crisp because this unit vector has a time dependence. So how do you write that? So we have to consider like we have to consider how this frame is constructed. We have to do some math. So initially, this is where R hat points, right? Afterwards, so I'm just zooming in really big. I'm just zooming in really big here. Because over here, where R hat points, so where theta hat points. So yeah, and then these things all have unit one. So I'm just like magnifying this, zooming it out to be this one. So when you change theta by a little bit, when you let time pass by a little bit, because remember, we want to find the time derivative. What happens in a short amount of time? So R can change, it might get further away from the origin. That's what we accounted for. This is what we accounted for here already. One other thing that might change is the directions of R hat. So since we want to find the R hat dt. After you let a little time pass, this is essentially going to be rotated, right, by this little d theta, and this will be the new r hat. So dr hat dt is gonna be also remember ourselves what the definition of a derivative is. The derivative is the difference between the new one minus the old one divided by the change in time. So what is this new minus old? It's just this vector, and then you realize that, oh wow, that's just the theta hat, right? That vector points in the direction of theta hat. And what's the magnitude? The magnitude is theta hat d theta, right? Because number one, it points in this direction. This direction is just theta hat by definition. And why is the magnitude d theta? Because the magnitude of r hat is 1, and using the arc length formula, s is equal to r theta. This length s, this length s is just going to be r theta, but r is just 1, theta is just d theta. So that's why the length is just d theta. So it's theta hat d theta dt. So this is going to be theta hat d theta dt. And sometimes you write this just as theta hat theta prime. So this is going to be r hat, so r prime, r hat plus r theta prime, theta hat. Right, so this is what we call the tangential and radial velocity. This component here is the radial velocity, and this component here is the tangential velocity. So you can see that right from the definition of a polar coordinate. Okay, what about acceleration? So we can go one step further and talk about acceleration. So, the wrong color. D squared P dt squared. It's just going to be a time derivative of that. So let's apply the product rule again. The product rule says that it's going to be r prime prime r hat plus r prime r hat prime. So that's the first term. The second term is going to be r theta prime prime plus theta hat. Sorry, theta hat plus. Yes, it's a little bit of algebra, but you can see it. Okay, we see another problem now. Just now we got um r hat prime. How do we get theta hat prime? So theta hat prime can also be obtained by a similar argument. I'm not going to go through it here, but just know that theta hat prime, you can show that's equal to negative r hat theta prime. So remember, the point here is to say that the point here is to say what directions everything changes in. So we try to make sense because like if you think about it, at some random angle theta, this is going to be r hat and theta hat. When you change the angle by a little bit more, theta hat is going to go downwards and r hat is going to go upwards, right? So that's just like when I say upwards, it's not really upwards, it's relative to, so if you do the math, you'll work out to be this. So it kind of makes sense. So it's going to be r prime prime r hat plus r prime theta hat. It's going to be r prime theta prime plus r theta prime prime theta hat plus. Just expanding everything, substituting in the time derivative. And then lastly, I can collect terms. There we go. So that's acceleration in polar coordinates. It's a little bit tedious, but we can call this A as well. We can call this V as well. It's the same thing as this. So this V, and this V, they're both the same V. They represent the same thing in physical space. They represent the part of velocity of a particle. Why do they look so different? The reason why they look so different is because the universe doesn't give a shit about what coordinate system you choose. It only, it only cares about the vector itself. Like it only cares about the magnitude and the direction. It doesn't care how you describe it. It doesn't care what coordinate system you use. It doesn't really care if you use r instead of rho. Because I know some textbooks use rho theta instead of r theta. It's kind of like, I don't know. Well, it's like it makes sense, but it's kind of cursed. Um, Yeah, so same thing over here. This acceleration is going to be the same as this acceleration that you can get from here. It's just that it's in a different functional form. Like, as like someone who uses these tools, like, this has a different shape than this, even though they are the same thing, right? So this thing on the left is called the radial acceleration. And this thing we call the tangential acceleration. So I think I'm getting tired of this theta prime prime thing. So let me introduce a few more variables. Let's go into the rotational case. In a rotational system, but before that, is everyone okay with this math that I just did? It's a bit sus with the taking time derivatives of a unit vector, but it works. What do you mean, Brandon? So, anyways, in a rotational system, just like how in the later case we have position, no, it's not even spoilers, I just don't know what you mean. Uh, so you have a position vector, you have a velocity vector, and acceleration. In the linear case, in the rotational world, we have a similar thing. We have data as a vector now. Remember data, so like a new thing, something that might be new to people is that data is a vector. Um, the time derivative is the angular velocity. The second time derivative is the angular acceleration. So note that we use omega for velocity and alpha for acceleration. I mean, it's convention again. So where does this vector point? So we use this thing called the axis angle representation. It's a fancy name, but what it says is that if you is to use your right hand again. If something rotates counterclockwise, if something rotates counterclockwise, you put your hand in the original direction of rotation. So you put your four fingers over here. You close it into this direction, and then you see that your thumb points upwards. So you put your hand there in the horizontal direction. I mean your right hand there. Don't use your left hand because that like kind of fucks everything out. You put your right hand in the direction. You close your hand into the new direction, and then your thumb would point in where theta vector should be. So this theta would be this theta hat, even though it's a different theta hat. And so these are not the same theta hats. Just keep in mind, these are not the same theta hats. You know what? Maybe IJK is a good. Never mind. But like, you get a point. Like, it's just to say that, like again, like I really want to drill home the idea that like you can do you can do without this coordinate system. Like you can always use something else. Um, it doesn't really matter. The vectors are still vectors in space. These vectors, at the end of the day, there's just gonna be arrows in space. They're gonna be arrows in 3D space. They're gonna like if you live in a real world, which as a physicist you should, because you know you want to model the real world. If you live in the real world, um, vectors are just gonna be arrows in space. You have to hallucinate them in like 3D space. So like this is a vector. Yeah, so schizo posting. Anyways, so um yeah, so that's axis angle representation. But rewrite this, it's gonna be r prime prime minus r omega squared. So if I don't write the vector, if I drop the vector, I mean only the magnitude. So that means I only talk about the magnitude of omega here. Make more space. Okay, I'll take a time derivative, you get this. Take one more time derivative, you get this. Same thing for position, linear for the linear case. Okay, so copying down what we have just now. This is the radial acceleration. This is the tangential acceleration. Okay, something I want to draw your attention to is what happens when there is zero radial sorry. So what happens when there is zero radial acceleration? When something's in constant circular motion, when something's in like perfect circular motion, what is the radial acceleration? Because when something is in circular motion, right? When something is in circular motion, it doesn't get out of the circle, is what I'm trying to say. So that means that it doesn't accelerate in the radial direction. Radially, it doesn't move. The point stays on the circle, so it doesn't move in the radial direction. So that means when something is in circular motion, when something is in circular motion, that means the radial acceleration is equal to zero. And what does that say? That means that r prime prime is equal to r omega squared. What is this term? We call this term the centripetal acceleration. Cool. So yeah, that's one way that you can derive the centripetal acceleration. I'm pretty sure you guys have seen it in high school SPM. If not, like it's still not too late. But yeah, this is the centripetal acceleration. Um, so even though something is in circular motion with constant velocity, if something is in constant velocity in a circle, doesn't mean they don't have an acceleration on them. By definition of being in circular motion, you have to have a centripetal acceleration, as we see here. Okay. So any questions on that? It's a little bit mind-bending. Circular motion always, makes people's head spin. Okay. Let's see. Okay. So if there's no more questions, I'll move on. But R is the magnitude, yes, R is the magnitude of the radius vector. And R prime prime is just a radial acceleration. Ah, yes. Oh, sorry. My bad. So yeah, this is the part where notation is a little bit funky. You're right. Okay. So what Wonkai is trying to say is that R here, this R here is the rate is the distance to center. So yeah, it's a little bit confusing. I should have not used R prime prime. You're so right. Sorry. Let me rephrase that. R is constant. And radial acceleration. is equal to negative r omega squared. Sorry, yeah, you're so right. My bad. But yes, this is the result that I was trying to allude to. Yes, so r is constant. Thank you for clearing that up. Yeah, it's my point is that it's a centripetal acceleration, and it's not zero, even if like the time derivative. So in constant motion. So let me just write the full formula. So in circular motion, r is constant and omega is constant. If like I mean if something moves in like uniformly in a circular motion, so uniform means that omega is constant, and circular means r is constant. So that means the total acceleration will be 0 minus r omega squared plus 0 plus 0. So at the end of the day, it's just negative r omega squared in the r hat direction, and that's the centripetal acceleration. So yeah, cool. Thank you so much. Any questions on that? Okay, cool. So let's move on to the next part where we can talk about reference frames. So let's remind ourselves what the topic of today is. Um today's topic is kinematics and statics. Reference frames. So you can always choose a reference frame that's convenient for you for the problem. So you can move. So when something moves, okay. So before that, I want to define something called inertial reference frame. So what does the inertial reference frame mean? Inertial means like things are so inert means something that's like not changing. Inertial reference frame means that your velocity is not changing. So when you say something is inertial, you see that their velocity is constant. Um, because they're inert to change. Their velocity is constant. Why velocity? Like it's the whole history, but it's velocity. Um, so that means that whenever you have something that's moving in a so whenever you have something that's moving in a constant velocity, both when you have something moving at a constant velocity, you can always change it to the reference frame. You can always change it. So let's suppose this thing is moving to the right with speed v. So it zooms past your screen like this. It zooms past your screen like this. You yourself can move your head together with it. You can like change your reference frame, move yourself with the particle. You'll see that this particle will have zero velocity in its fate. The particle will be at rest in the new reference frame. So reference frames are something. It's like a coordinate system, and this change in coordinate system, like don't worry about relativity yet. That's like the last week, so just don't worry about it. What we should worry about is Galilean transform, which is to say that um, when something moves to the right and you move to the right together with it, it doesn't move in a reference frame. So uh, can always plus or minus v to shift reference frame. And what happens when you shift the reference frame? So suppose you're like sitting on the street. Suppose you're walking on the street. Sorry, you're sitting on a bench on the street. And the car drives by. You would think that only the car is moving. Everything around you, the trees, the bench, the houses, they're like sitting still. But in the car, when you're moving with that velocity, you're in a new reference frame, and everything around you moves to the back. So that's you either move forward in life or life moves past you. So so that's reference frames. And everything else around you has to like change by the same velocity. Cool. So this is a dangerous idea. The reason why this is a dangerous idea is because there's so many ways that you can use this to simplify problems, and like solve them more easily. So what I mean by this. So there's a very popular problem called pursuit problems. Popular class of problems at least. So pursuit problems. Suppose you have this, yeah, so this problem is going to also be on the handout, but suppose a rabbit begins at the origin. Rabbit begins at the origin. Suppose R. And the fox begins at point 0, -8. So there's a fox. And there's a fox. So there's 0, 0, 0, -A. Suppose the rabbit starts running to the right. At the same time, because the fox always chases the rabbit, it always moves towards the rabbit. So this moves with velocity v, moves with velocity v. After a really long time, you kind of think you can kind of see that the fox is kind of like drag. So like if you imagine this playing out, so if I draw this, so this is the xy. So let me draw the coordinate system. Actually, no, let me just, yeah. So over here, the fox will still point in this direction. Over here, the fox will point in this direction. So you can kind of see that the fox is being dragged along by the rabbit, right? By the setup. Suppose you have this system where you have a rabbit moving to the right and the fox like pursuing it. So this is what we call a pursuit problem. You can always so after a really long time, the rabbit and the fox will just follow each other on a straight line. If a constant separation vector of like after a really long time, they're just gonna be separated by some distance d. Fox, the rabbit. So the question here is that what's the final distance d? So this is initially a, because 0, -a. So what's the final distance d? That's what we're trying to find. So you can give it some thought. You can give it some thought, um, and you can realize a few things. If you think of the right, if you think of the right, if you think of the right reference frame. So let's see. Oh wait. Oh wait. Yeah. Sorry. Wait. Let me just fact check myself. Oops. Sorry. I'm not sure why I pressed that. Okay, wait, sorry, yeah. Okay, so this is okay. Okay, so Let's just okay. Should I explain this with or without? Okay, wait. So first, the rabbit always moves at the velocity v to the right, right? So we can shift into the rabbit's frame. And how does that give us? Like, what does that give us for the fox? So for the rabbit, if you shift everything to the left, if you shift into the rabbit's frame, so this is initially the setup. If you shift into the rabbit's frame, the fox will move like this, right? The fox will move like this. There's a B, there's a B, V, there's a V. So that means that it moves in this direction. And then after a really long time, what happens? After a really long time, um, wait, sorry. Can I simplify this more? Okay, well, okay. After a really long time, they're still gonna be separated by this distance D. Um, and so yeah, so like at the end of the day, they're gonna have like um, zero relative velocity. So like at the end of the day, the fox will go from here. The fox will go from here. It'll move in this direction, and then after a long time, it's gonna end up here. It's gonna end up here. This kind of thing. So the question we want to find is what is this final distance D? Hmm. Yeah, this is not just A, because they get closer and closer, but they never reach. So okay, let's see. Okay, so hmm, okay, so I think this is the wrong reference frame to do this problem. One reason why I say this is because sorry, I wrote this down last night and I was like, I think I can solve it, but I think it's not that simple. So okay, the reason why I think it's the wrong reference frame is because this particle here starts moving with a velocity, but then ends up with no velocity at all. So there's some acceleration going on there, which is a little bit hard to control. Acceleration's always a little bit hard. Since this is all an inertial reference frame, like since you want to shift into a inertial reference frame, it's best if you shift into something that has like symmetry or still has something that stays constant, stuff like that. So that's why I think this is a wrong coordinate system to use. Let me try a different approach. So dB. Suppose at some general time, suppose at some general time, the angle between the fox and the rabbit, the angle between the fox and the rabbit, um, is theta. So what's the displacement between them? So remember, we want to find so we want to find this like the separation as after a really long time. Suppose we call this R as R rabbit minus R fox. So how does this velocity vector change? So I said like this dr dt, how does it change? So number one, so the change in the size, the change in the magnitude of r is just gonna be v minus v cos theta. Sorry, negative v minus v cos theta. So why is this? Because the relative velocity between them, the relative velocity is gonna be v cosine theta. So this is v, this is v cosine theta. So what you get, the difference that you get is gonna be dr dt. Um, but since we know that this radius, the separation vector always like decreases, that's a negative sign up here. You could also write this in terms of if you really want to, you could write this in terms of like you could shift into the frame of the rabbit, and then so you could shift into the frame of the rabbit, and then say that this it's like this. So if you shift into the frame of the rabbit, um, the velocity points to the left. So the net velocity here is just going to be negative v plus this v cosine theta. So hopefully that's clear. Something else that might also change is the position of the fox. So how does the fox position change? Uh, well, the fox position changes by hmm, fox position changes by it's v minus v cos v minus v cosine theta. Yeah, sorry. So um wait, is it really? Starts here. Yeah, so like suppose you have the wait, yapping too much, not enough thinking. Mm, okay, it's gonna do like this. Suppose this is gonna be some vector x and y. The x component of the separation, the x component of the separation, which is in this direction, the x component of the separation, um, is this, and the radial, hmm, radial component. Oh, the radial component is gonna be v cosine theta minus v. Okay, that makes sense. So why this makes sense is because um if if you let time play by a little bit, if you let time play by a little bit, after a short time dt, after a short time dt, mm, This thing's gonna go here. So how much did it change by? It actually changed by. So let's copy this. Put this over here. Shit. This thing's gonna go here. It's gonna go here. Hmm. Actually, I think it's best if I leave this problem afterwards, and I'll give you guys a write out afterwards. Because I think I'm just making guesswork here. Ugh. What is this R then? Okay. I think it's a great problem. I think you guys should think about it in your own free time. I am gonna say that at the end of the day, the distance between them is gonna be d over two. Just I did this a long time ago. I don't remember this. Um, so yeah, like I think it's best if I come back to this in future. But yeah, my bad, guys. I will send you guys a write-up afterwards. But yeah, off the top of my head, I just can't remember how I did it. Um, I'll just show you guys another example of relative velocity reference frame. So let's see. Yeah, so I think so. Well, reference frames is the main point here. Like, let's not forget what we're here for. So one type of problem is pursuit problems. I think if you choose a suitable reference frame, it's gonna be easier. But I just off the top of my head, I just can't remember which reference frame it was. Um, but yeah, like there's a simple solution to this that doesn't involve vectors and stuff. Um, so I think wait, why don't I take a 5 minute break and let's come back to this problem because it's at nine. It's at a 9 p.m. point. Let's take a 5 minute break and let's come back to this point. And I'll just like keep solving this. You guys can get the drink of water, and I'll tell you guys what happens. So hopefully you guys are already doing that. Let's come back in 5 minutes. Hey, hopefully you guys had time to come rest and come back. I realized my solution. I realized what I was writing about. Because I have this like piece of paper that I have this receipt that I still have around my notes on. I just did this calculation last night. Just don't remember. Now I realized what I was doing. So my bad. Yeah. So okay. Let me restate this. The pursuit problem is nice because it's a nice little problem that like lets you think of reference frames, like who's moving relative to who, right? So sometimes reference frames like might be straightforward where you just like shift into that frame, just like this. Sometimes it might be a little bit more subtle. And this is a subtle case. So the reason why I like was thinking about like, R and XY was because classically, if you trace out the path of the fox, if you trace out the path of the fox, it's gonna be a tractrix. Tractrix. So let's see. Tractrix. And it has this it has this it has this property where R plus X is constant, where R is the separation from it um of it from like um the the rabbit, and X is the horizontal component of that. So yeah. Anyways, using this XY coordinate system, if you define this data as something that like something that changes in time, because at first data is like at first so data is defined to be the angle between the velocity of the fox and the velocity of the rabbit. So at the start, data is like 90 degrees. So data slowly decreases until like data is equal to zero. So I just randomly call this thing data because it's easier to resolve the forces this way. Um, since the rabbit always moves to the right by velocity v, it's a nice thing to use the rectangular coordinates. That's why. Um, so if you write down the separation, um, and the thing about reference frames here is that in this rectangular reference frame, the x component of this separation is going to change by this much. But in the reference frame of the fox, when it's chasing the rabbit, there's a line of sight. When it's chasing the rabbit, the relative velocity of the rabbit and the fox is actually just v cosine theta minus v, right? It's v cosine theta, so it's this component of the rabbit minus v. So that's the component of the radius. And so by the setup of this problem, if you add them together, you realize that like the change is zero over time. So this is a conserved quantity. So this is a conserved quantity, and therefore you can write the initial r plus x is equal to the final r plus x. The initial r plus x is just a, because r is equal to a and plus zero, because there's zero x separation. There's only the y separation, and that's equal to d plus d. Because at a really long time, the separation between them is just d. So therefore, d is equal to a over 2. Yes. So yeah, that's how you can solve it. And that's the reference frame part of this comes from writing this down. The reference frame part comes from writing this down. Okay, I must admit though, that was a really bad example, now that I think of it. So let's look at a better example. So when you say reference frames, you can do a few things to it. Like when you want to shift reference frame, you can like translate with the frame. You can accelerate with the frame, even though that might cause some non-inertial accelerations. Um, like for example, if you're sitting in the car accelerates, you get jolted backwards. We'll talk about that in the future. But yeah, you could like translate into the frame with constant velocity or accelerate into the frame or even a rotating frame. But for this one, like you can also just rotate the whole frame. So what I mean by that, okay, if you have an inclined plane and you throw a projectile, if you have inclined plane, you throw a projectile. and they ask you like, what's the range here? What's the distance here with the range? What's this distance S here? So it's a little bit complicated. I mean, you could do it without changing reference frame, but if you do change reference frames, you can realize that you can tilt the whole thing by you can tilt the whole thing. So you can tilt the whole thing, right? So now this angle becomes theta plus phi. But now the gravity is also tilted because normally gravity points downwards, right? Normally gravity points downwards. Now gravity points in this weird direction. That's that has an angle phi here. And now but then again, the nice thing about this is that you can use your classic ways to solve. You can use your classic ways to solve this like XY kinematics problem. You can just use like G cos phi and G sine phi, and so like it's easier to like perform the calculations. This will be in the handout that I'll give you guys. So like try this out when you have time. I think that's a great example, but I don't think I'm gonna go through it here. Even though I did go through a really bad example of the pursuit problem. Okay, last thing. Trajectories. I think the reason why I put a pursuit problem there was because I wanted to segue into trajectories, which is like paths traced out by objects. So let's see, last thing, paths traced out by objects. So in the pursuit problem, you see that the path of the fox is traced that's traced out is called a tractrix. Um, there's a property associated with it. Mathematically, when you have this set of points that like lie on the trajectory, the fact that they all lie on the same trajectory means that they all share the same properties. All these points, so suppose you have a parabola. So this is a little bit more of a math thing. So suppose you have a parabola. I'm going to ask you guys a question. Why is this point on the parabola and not this point? Well, I mean, of course, you can say, oh, my line goes through it. That's why. Well, that's one way, but why does your line go through it? So the reason why this point here is on the parabola is because it satisfies some things. It satisfies the fact that the y component, is equal to x squared. Like when you write down y equals x squared, you're saying that all the points on this parabola, the y component is exactly equal to x squared. So that's why this is not on the parabola, because the y component is not equal to x squared. So, as a computer scientist, if you want to write a simulation to plot a graph, you can just like, well, that too, like, so Brandon said that, so there's a few ways you can do this. You can do it with geometry, you can do it with algebra, you can do it with algebraic geometry. Well, you can take that at some point, but, so the point is that like there's some things that all these points satisfy. So as a computer scientist, if you want to simulate a graph, if you don't know how to write a graph plotting software, like um, if you want to write a like graph plotting software, but you forgot to like how to plot graphs, something you can do is just given this XY plane, just test out like a gazillion points. Like test this point, this point, this point, this point, this point, this point, this point. You test all the points on the screen and then check which ones satisfy y is equal to x squared. And then you will still get a parabola. So that's that's a funny way to like plot graphs, but it's a correct way to think of it. Um, so yeah, so a common trajectory that you'll see is the projectile motion. So let's see. Let's derive a projectile motion. So sorry, you need this. Well, maybe I'll just put it here. So suppose you have a projectile starting at the origin, gets fired, so negative v naught, angle theta, and in the presence of gravity g. So um, if I resolve into x and y components, um, if I resolve in x and y components, um, the acceleration is just going to be equal to. So suppose I write the position as x, y. The acceleration is going to be negative 0, negative g, because my y is pointing downwards. My velocity, so acceleration is the derivative of velocity. So velocity is going to be, so this is my velocity, the integral from 0 to time. So this is going to be v minus v naught equal to a t. So v is equal to v naught plus a t. Uh, I'm just using this definition. A is equal to dv dt. I integrate it, plug in the boundary conditions, and yeah. For now, this is just, so what's v naught? V naught is v naught cosine theta, v naught sine theta. So yeah, as expected, the x component doesn't change. The y component changes by negative gt. Okay, what's the position? So the position, it's gonna be the same thing. You integrate from the initial position to the final position. That's gonna be equal to 0 to t. So notice how like I'm using this dt prime as the integration variable and using the time as the actual final integration variable. Like you can also just do this if your own way. Like I'm just doing this integration quickly. Um, so I'm not gonna show like the power rule and stuff like that. Um, Also hopefully you guys are okay with using vectors as like using vectors in integration, because essentially what you do is like do it component wise. You can do integration component wise. Um, so yeah, like, I think I like this derivation because it's like a speed run way to like do both components at once. But yeah. So anyways, this is gonna be P minus P naught. This is gonna be E naught cos theta t, E naught sin theta t minus half gt squared. And since P naught is just 0, because this thing starts in origin, therefore, this is the x and y, the position. Cool. So that's cool, but how does that tell us about the trajectory? So the reason why I didn't really like, so I mean, I think you guys can do this derivation on your own. You guys have the tools from SPM, whatever. So maybe I'm just showing you guys another way to do it with vectors and like, anyway. Anyways, the result should be familiar. What I want to guide you guys to think about is what defines this trajectory. Because we know from like SPM, whatever, um, this is gonna be a parabola, right? But how is it a parabola? So when remember here, like just now when we said y is equal to x squared, we say that every point on this parabola, every point satisfies this thing. So based on these two equations, y and x, can you write an equation that's always true for all times? Can you write an equation that's always true for all times? And the reason it turns out that you can. So it's quite trivial in this case, but we'll see in the generalization later. Um, that it might not be that trivial. So okay. So let's see. Make a new page. Okay. So so let's remind ourselves of the goal here. Like, because this thing at every point in time, so just like how you can like sample points along this parabola and like ask yourself, is this y equals x squared? Is this y equals y? Is this y equals x squared? Is this y equals x squared? So like you can do that. Same thing over here. You can ask yourself like at this time, at this time, at this time, at this time. Like is the particle gonna be here at this time? Is the particle gonna be here at this time? So um yeah, so the time is something that like you parameterizes the trajectory as one says. So one way you can do this is say that since y is equal to v naught sine theta t minus half gt squared, x is equal to v naught cosine theta t. If you want an equation that's true for all t, if you want an equation that's true for all t, then you just like replace t with that thing. So this is gonna be x over v naught cosine theta. So yeah, just like replace t with x over v cos theta and minus half g t squared. So this equation that I just wrote down, since I substituted time t for like that thing, this is gonna be true for all times t. And this equation is gonna be the parabola, the trajectory. The trajectory of the parabola. And this equation is true for all times. The reason why I keep emphasizing this is because I think it's a it's a mind like you have to like make sure you know like so this is a good example like that's familiar that shows you guys like how trajectories can be formed. You want to find an equation that's true for all points for all times, and normally what it boils down to is like substitute the time for something else, like eliminate one of the variables. Okay, so let's see. Okay, something cool about this is that like if you have this parabola, um, if you know the trajectory of one parabola, oh, sorry, wait, let me formulate this motivation quite in a new way. Suppose now like again, right? You know how one parabola at one v naught. So let me highlight this. I forgot this v naught. Sorry. If you want, so given one theta, one g, one v naught squared, you will deterministically know how the parabola looks like, right? So just like how just now, given um given from just now, given one v naught, one theta, one t, and one g, you can know where the point will be. And uh, now that you do this like envelope calculate, like the trajectory calculation, if you're given like a theta, a g, and a v naught, you can know points. You can know how the whole shape looks like. Now I want to ask, like, given um, g and v naught, how does the envelope of all parabolas look like? So notice here that we're reducing by another variable. So initially we have four variables. Initially we have four variables like v naught, theta, t, g, and then we reduce it down to three. Why is that? So because we don't really care about the t anymore. Like when we say like across all times t, across all times t, like we look at the whole trajectory, we effectively reduce by 1 degree of freedom, right? Like if you don't care about time, then you just like miss out on time. So like you miss one parameter. It's like that's nice. Now, if you want to ask a question, how does the envelope of all parabolas look like? You're effectively reducing by another dimension. You like um you eliminate this dependence on theta and like as well. So if you have a slider, if you have a slider for t, the way you generate this is that you have a slider for t, you like slide this t from 0 to infinity or whatever, and then you get the path traced out by the point, right? Because like you just like slide theta, and then like all the points that theta passes through, you just keep down, and that will be a trajectory. Similarly over here, if you want to find the envelope of all parabolas, you play the slider for theta. If you play the slider for theta, you will get a diagram that looks. Now let me pause this. Oh shit. Eh, let me bring this image back out. Sorry, hold on. It's in the handout, but I forgot to put it. Okay, it's here. Share. Nope, my bad. Share. Nope, not that. Share. Green. This. Okay. So this was the image that I wanted to. Yes. Okay, sorry guys, that was not prepared. Okay. So, um, this is the origin point, right? This is the origin point. If I fire projectiles from this point, given like a constant velocity, but I don't know the direction, like so just like here, I fire a projectile from the origin and I ask you where it's gonna land. I don't tell you what the time is. Like you just have to figure out that, oh, this equation holds for all times. So now that you have this like new dimensional another dimension, sorry, a higher generalization. If you know the initial velocity, but I don't tell you what the theta is. If I don't tell you what angle I fire it at, then you can still you can still see that there's some things that you can say about the system. You can say that the system is always bounded above by this safety parabola. So this is called a safety parabola. And so this goes into a family of curves called envelopes. So what I mean by envelopes? Okay, so let me do some like sus math real quick, and I promise this is gonna be the last part of the lecture. So I'm gonna spend a little bit more time on this. It's not well, I don't think it's gonna show up that much in Olympiads, but I don't think it's a really cool curiosity that you can explore. It's also the reason why like when you have when you have a like mug, so you know how like you can see a card. So you have when you have a mug, like you can sometimes see like a cardioid, a love shape in your cup because like the light all like converges at the same point. It's beautiful. Um, so you can use the same math for that. But I just thought it would be cool to tell you guys about this. So an envelope you can find it with a contour function. So what do I mean with contour function? Remind ourselves again. How do we define this y equals x squared? How do we define this line? This line is defined for all points that satisfy y equals x squared, right? We could rewrite this as a function of x and y, such that whenever a point is on this line, this f is equal to 0. Right. So this is a contour function. So like is that clear like how this function like comes into play? So this function comes into play by just rewriting the initial conditions. The initial conditions for a point to be, so this comes around by rewriting the conditions for the point to be on the line. Um, and if a point is on the line, that's equal to zero. If it's below the line, it's equal to negative. If it's above the line, it's positive. So let's see, if f is equal to 1, then y is equal to x squared plus 1. So that's going to be something like this. Does that make sense? So, and these are called contour functions because every value f, so so f is equal to 0 is one curve, f equal to 1 is another curve, f equals 2 is another curve. So it's like a contour plot. So contour. Um, yes. Something else about this function is that well, so let's just write the contour for this. So suppose I only talk about one. Suppose I only talk about one parabola. Now I want to find the equation for the safety parabola. So the goal here is to derive this black line. The goal here is to derive this safety parabola. How do you do that? Um, so okay, every point on this like safety parabola is also a point on some other parabola, right? Every point on this parabola is also a point on some other parabola. Suppose so, for example, this point is on this parabola. This point here is on this parabola. So you have like every point on this safety parabola was also once a point in some other guy's parabola. So that's one thing you can write down. So suppose the envelope is x and y. Uh, then the contour that you can write for this is for the condition of a point to be on the parabola. The contour for this is that the y minus. So I'll just call this like y x theta lah. It's easy to write. Y minus some function of theta and x is equal to 0. Right, and like so this like really big complicated function like y x theta is like, so I'm just gonna call it like big Y. So it's yeah. So at some point on this safety parabola has to satisfy this equation for some x, some y, some theta. Okay. So and then one more thing is that this is only tangential at one point. This is tangential only at one point. So if you change this point by a little bit of theta, which we're doing here, is like remember, all these points, all these parabolas are generated by changing theta. All these points are generated by changing theta. So that's theta small, theta big. So like every point, every parabola has a different theta. So if you change the theta by a little bit, it's not gonna be on the parabola anymore, right? It's not gonna be on the parabola anymore. Because like um every point in this parabola has this like really specific data. Um well it's gonna be close to the parabola, but it's like, so if you change the data by a little bit, it's gonna be close to the parabola, but it's not really on the parabola anymore. Um so what I mean by that is that it's like it's gonna be tangential, is what I'm trying to say. It's gonna be tangential to the parabola. So again, I'm doing this thing where I forgot what I wrote down last night. So I wrote down the equations. I was like, what does this represent again? Let me do this thing of shit. Right. So yes. So it's gonna be yeah. So it's gonna be tangential to the. So if you take this original function and you differentiate it by theta, if you take this original function and you like change theta by a little bit, this thing should not have changed much, right? Because all these thetas. So I think just now I was like kind of using the wrong words for things. Let me rephrase things. So um all points, all points on this parabola, even if you change the theta by a little bit, it will still be on the it will still be on the like it will still be on this parabola, but the point's gonna shift. So just now when I said like it's not gonna be on the parabola, like it's like it's not gonna be on this point anymore. It's gonna be changed to some other point. So suppose you have this like initial theta, it intersects the safety parabola at this point. When you change the theta by a little bit, it's not gonna be at this point anymore. It's gonna be some other point. So I was using bad phrasing. I'm sorry about that. But yeah. But what doesn't change is that regardless of how much you change data, regardless of how much you change data, there's still gonna be some point that touches the parabola at one point, right? Like no matter what data I'm at, like and no matter how much data I change, um this like there's always gonna be some point that satisfies there's always gonna be some point that satisfies this, which is to say these are all at the minimum of this function. Um, these are all at the extreme of this function. So the partial. So when you change data by a little bit, the this doesn't change. This function, this y of x data, this thing doesn't change because this describes each and every parabola. And when you change data by a little bit, it's still going to be a parabola. So the partial is equal to zero. So yeah, like, let's try to do this math and see what you get. So when partial y partial theta is zero, x secant squared theta minus what was this? Secant theta is just secant theta tangent theta. It's equal to zero. So that means that tangent theta is equal to u naught squared over g. Right. So the secant squareds cancel, twos cancel, x cancels. Yeah, u naught squared over g. Cool. So I can put this back into this equation. Um, hmm. So secant squared is just secant squared is just cosine squared. It's just 1 plus tangent squared. Yes. Yes. So and then you do the math, you get something else. But just notice that this just like I mean I like it doesn't really matter like how you simplify it. Like this equation that you get, um this equation that you get is um yeah the safety parabola. Wait, Brandon, what do you mean? Sorry, I don't think I get your question. Okay, so let's explain this a little bit more. I think yeah, let's explain this a little bit more. So partial y partial theta is zero because when you change theta by a little bit, when you change theta by a little bit, um, the points is still gonna be on the parabola and on the safety parabola. Like as in, there's still gonna be a solution to this, right? So, as like this whole this whole big Y function is still gonna have to hold. Still gonna have to hold. Um, so that should still be true. Because okay, let's think of it like this. Remember how just now we have this contour function? When you change things by a little bit, it still has to be a contour function. Right, so suppose this and parameterized by another, let's say a. So there's like y minus ax squared. When you change f by a, when you change f by a, this should still be a contour function, right? So okay, let's see. Okay, well, actually no, I think that's the same argument. Okay, let me think of another argument. Um, okay, suppose I write what I is some function of x theta. This parameterizes all curves, right? This parameterizes all these curves, like this curve, this curve, this curve. It parameterizes all curves. The envelope, the envelope is defined to be the point where it's the supremum. It's the highest point at that x. So given this one x, right? Given this one x. So suppose I say like, okay, I want to find like what point. So to which parabola corresponds to this point on the safety parabola, given that I'm at this coordinate x, right? So the envelope is gonna be the supremum. It's gonna be the highest point of all the datas. So let's see. So so as in you can look at this parabola. Oh sorry, I erased it. Let me just zoom in real quick. Unlock the zoom so it can be consistent. But suppose I look at this one point here. I could say that, okay, maybe I could look at this parabola and see if it's the highest. And no, it's not the highest because you see the parabola is quite low. So it's not this parabola. What about this parabola? Oh, you're getting closer. And then you keep changing data by a little bit. If you keep going by data, if you keep going by data, you get the optimal data where it exactly touches the safety parabola. And then you keep going by a little bit. Oh no, you're not touching it anymore. You're going you're like you're going down. So like yeah, so as like what like when you vary this data by over all its values, when you vary this data over all its values, you get an extremum point, and therefore when you vary by only theta, this y achieves a maximum at that fixed x. So that's what this partial derivative is trying to say. At that fixed x, this thing is going to achieve a maximum. That's why it's like partial is equal to zero. So yeah, anyways, the point here is that like you can do this math to get envelopes. So like if you have a family of curves, if you have a family of curves parameterized by some variable, be it time, be it data, um, you can generate a family of you can generate a trajectory or like an envelope that's tangential to all these to all the trajectories. Um and yeah, like as in it only touches everything at one point. So yeah, and then basically this is all called envelopes, and there's this whole study about it. You could it's like it's not gonna come out in the Olympiads. It's just something cool. This safety parabola has come out in the Olympiads. This is one way to do it. This is one way to get the safety parabola, but it's not the only way to do it. There's many ways to do it. But yeah, um, cool. Do you guys have any questions right now? See, what else can I say about this? Okay, okay, awesome. I was responding to some messages. Okay, last thing is statics. Because remember today, we've been talk so the thing is like today's session on statics is gonna be a bit more short because it's mostly gonna be review for you guys. It's on the handout. Um, but for statics, I'm just gonna like I'm gonna like concentrate on the main points. It's like this like short 10-minute section is that in linear cases, forces are the things that push and pull. And if you're static and you're not moving, no forces push and pull. So all the forces added together is zero. In the rotational case, torques are the things that make it turn. If you don't turn, then you have zero torque. Um, you can do like anything you can do in a force problem, you can also do in a sorry, that's not what I mean, but you can do a problem without ever defining a torque, but that's gonna make your life so much more harder. But it is possible. Um, so let's see. And maybe one last thing that I mean it's on the handouts. I recommend like you guys go to the handouts because that's like I selected a few problems from like places and took away some like not important questions, put in some important questions. Um, but yeah, one last thing that's like really confusing about statics is friction. So, uh, friction. Suppose you have a surface, you press on it. The more you press on it, the more friction it's gonna have. So, when you say press on it, what like so when you say press on it, uh, you're giving it normal force, right? Because the surface is pressing back. So the harder you press on it, the harder the surface presses you back. And so the friction is going to be a little bit more. So like, as in like, this thing is trying to move, but then if you press on it, it's like it's jammed into the surface. And so like that jamming is called is a friction. And this friction um, can be written with this equation. And normally when you do questions with like friction lah, they assume this model of friction. Like I mean like you can assume this model of friction where this maximum point where this maximum point is this mu Sn, it's a static friction, and afterwards it's like some constant point, it's called the kinetic friction. Normally it's less than the static friction, but it's not always. Friction is a tricky subject. If they don't say, then you can just kind of like assume you can assume it's like this line. And like mu S is equal to mu K. So yeah, this is a common model of friction where like mu K is normally a little bit less than mu N. Um, yeah, I mean like yeah, just go check out the problems and especially the capstan problem and the band plate problem. I mean, you'll see what I mean. But yeah, thank you for coming. Um, well, sorry, that would be 2.3 and 2.4 in the handouts later. So yeah, check it out. Thank you for coming. Stick around for questions. Yeah, good luck. Bye.